Hi, folks. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from myself, Stephen Slaughter, and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to manage the question and answer session. If you have questions, you're welcome to put them in the chat window. But if you're not intending to speak, in the meantime, please just keep your audio and video off. Today, we're joined by our very own Bill Schultz. And Jeff, thank you so much for introducing Bill today.
Okay, thanks, Matt. Well, it's my pleasure to introduce Bill today. I feel fortunate in that Bill's been a friend of mine since he joined the USGS in 2002. And as some of you probably know, he just passed his 20-year mark with the USGS, so congratulations are in order for that. Bill's contributions to our program have been numerous and impressive. Overall, I describe Bill's research as cutting-edge field and modeling studies that are expanding the boundaries of our understanding of landslide processes and hazards. Bill isn't satisfied with just gaining a better understanding of processes. He works hard to apply that understanding to create applied landslide hazard products that help reduce losses from landslides. I think an excellent recent example of this fact is Bill's leadership in the Puerto Rico landslide project, which started following Hurricane Maria in September of 2017. Bill's leadership of this project has led to significant advancements in state-of-the-art techniques for assessing landslide and debris flow hazards. And he's also really pushed hard for broad acceptance of those landslide hazard products by local officials in Puerto Rico. A few other areas where Bill's made substantial advances include collaborative geotechnical testing and analyses of landslide materials with Kyoto University, and many collaborative INSAR studies with academic partners, as well as his ongoing studies on how expansive soils regulate landslide movement in Northern California. And with that, I'll stop and I'll turn it over to Bill. All yours, Bill.
Great. Thanks very much, Jeff. That's very generous of you. I appreciate that. And thanks, Matt, as well. And thanks, everyone, for joining us today. Today, I'm going to be talking about how shear surface undulations might contribute to shear resistance and partly determine whether landslides are likely to move rapidly or slowly. You probably notice on this slide, we have a picture, I've got a picture there taken by Mark Reed of the Oso, Washington landslide of 2014, and that's where this study started, but that's not my focus today. I'll touch on that very briefly in just a moment. First, though, I'd like to acknowledge the contributions from my co-authors, Ganghui Wang and Yao Zhang at Kyoto University in Japan, and Brian Collins and Mark Reed in California with the USGS, with the U.S. Geological Survey. Okay, so just briefly about the Oso, Washington landslide. For those of you who are not familiar, this occurred in 2014. And it's the second deadliest landslide in U.S. history after Mameas in Puerto Rico. This landslide moved about 1 kilometer across the floodplain in about a minute, and tragically killed 43 people and essentially completely destroyed a neighborhood that kind of existed in the foreground of this photograph on the left. I think Brian Collins and Mark Reed did a really nice job with the study that they performed, demonstrating that the very high mobility of this landslide largely resulted from, call it undrained, very rapid loading of alluvium in the valley, the river valley bottom by the landslide mass, which resulted in its liquefaction, which is somewhat illustrated by this photograph on the right, where this grayish sand and gravel is alluvium, essentially that was overridden. You see sand boils here and there. This is between hummocks of landslide deposit itself. So that's a really nice study, but we also know and wanted to determine why the landslide moved relatively rapidly from the hillside on which it formed in order to create such a loading condition on the alluvium. And that was the focus of the beginning parts of this study. We performed some advanced ring shear testing of the materials from the landslide and observed that the landslide materials lost significant resistance in some cases, and that potentially or probably contributed to the rapid movement onto the valley floor. But now let's get into this talk. I was just mentioning the rapid movement of Oso onto the valley floor, and the Oso landslide material has a lot of pre-existing shear gouge, as I'll mention in a minute. And shear gouge, if you will, or fault gouge, has been studied for a long time, and partly because it's long been recognized that landslides that form under gravitational conditions oftentimes reactivate catastrophically during coseismic loading. And I should say that moves slowly during gravitational loading can fail catastrophically, such as this landslide shown in the picture here. And laboratory tests on shear gouge have long shown that under rapid stress changes, some materials have display a peak strength. And after that peak strength is overcome, after a few centimeters or decimeters of displacement, the landslide can essentially move continuously, or catastrophically, I would refer to it as, under that same stress condition, gravitational stress condition. Lab tests have also showed that if you shear some shear gouges or fault gouges at increasing shear speeds, the material may weaken, which would result in accelerating landslide failure. And the contrary is also true. Some materials strengthen when they're sheared more rapidly, and some don't change strength at all. And this isn't just from landslide studies. In fact, a great deal of studies in the earthquake world have evaluated tectonic fault gouge resistance and observed very similar things. So we observed something similar at the Oso landslide, or with the Oso landslide materials, that they lost significant strength. And considering that we use some really advanced apparatus for our testing, and that this material from Oso was ideal for some testing requirements, as I'll describe in a moment, we hope that our testing could help to reveal some of the mechanisms that control these material behaviors. As I showed up there, but failed to mention, it's really largely unknown what controls whether a material, a gouge, is going to lose or gain strength or have unchanged strength during rapid failure. First, I should talk about shear gouge. I'm sure that many of you have seen and felt and been up close and personal with shear gouge at landslides, or perhaps in tectonic faults as well. And here are some photographs of shear gouge in the field or in the laboratory. In the center here, this is a ring shear specimen that's been cut from some of our Oso testing, and it shows a shear surface. We're looking down on that shear surface. If we flip that specimen on its side and look in cross section, that's this lower picture, and we can see that shear gouge consists of essentially a great number, a very large number of very closely spaced shear surfaces. And shear surfaces in shear gouge and also on rock exposures are often referred to as slickensides. Slickensides being essentially undulatory polished surfaces, such as you can see, especially in these lab results, but also these couple different landslides in California or Colorado, or this big, well, there's actually a series, but this large normal fault in the foreground here of this photograph at the Oso landslide. Within the shear gouge, we also know that particles are smaller, more rounded, and aligned with the shearing direction than are particles in the host material. And that's really just a product of comminution, just breaking down the particles during shearing, and chemical weathering as well. So generally you have a more clay-rich, clay size rich size distribution in shear gouge, but also clay mineralogy oftentimes as well, if there is some chemical weathering going on and there wasn't clay mineral in the first place. So let's talk about shear resistance real briefly. Well, at least a little background into it briefly. Essentially, I like how Terzaghi puts it. He puts it as though as shear resistance occurs because of geometrical interference to shear displacement, meaning things are in the way. So this little cartoon here of, let's say, a particle assemblage, and we're trying to shear it kind of in a right lateral sense here, or in a cross-section sense with the overlying material moving to the right. And if the plane of maximum shear stress is, parallel to these arrows, well, since it's a particle assemblage, there are particles in the way. So that's where you get your shear resistance. We also think of shear resistance on a landslide boundary scale. Here's a map of a landslide or part of a landslide that shows the landslide's moving from right to left. It shows the landslide narrowing in this area. So we have basically a restraining bend along this left lateral or this left lateral fault. And over here we have a releasing bend where the landslide widens. Those things affect shear resistance at that scale. And of course, we probably all remember from structural geology or from current practice at the tectonic scale as well. Here's a large restraining bend that steps as well in the San Andreas Fault. And those restraining bends are, of course, well known to cause shear resistance. So one thing that we thought was, well, perhaps we've overlooked a scale all along, and that is undulations along shear surfaces, slickensides, essentially. Would those not also provide some resistance to shear displacement? They should. They're larger than particles. They're smaller than other things, but still, there should be something there. So that was our primary hypothesis that we sought to test, that undulations themselves contribute shear resistance. And we know that undulations or this resistance that they may provide persists for long distances. In some cases, many of these striations that we see in landslide faults and tectonic faults might be carved by rocks or something like that, or just stronger parts of the soil matrix. Regardless, there's something that is deforming the opposing material, the material on the opposite side of the shear surface. So there must be some geometric interference involved there. In fact, we can go back to kind of the simple view from structural geology again and think about restraining bends. And what happens at a restraining bend? Well, we build mountains essentially because we're forcing higher stresses across that restraining bend. And then we form sag ponds and depressions where there are releasing bends along strike slip fault, be it tectonic or along a landslide boundary. With respect to how this might work for an undulation, well, here's kind of a cartoon cross section. So let's flip our plan view here into a cross-sectional view, but now we're also zooming way in. This is a particle system. Let's pretend this is the base of a landslide. And we have a shear surface here, and then a bump, an undulation. We'll call it a protrusion. It's sticking up, right? So if the landslide is moving from right to left, and this material here is essentially stationary, but it's left lateral movement, we have a restraining bend on the front or the leading edge or the side of the protrusion that is first encountering that overlying material as that overlying material moves, and a releasing bend on the far side or the back side of that protrusion. And what might we expect by analogy with these other systems, tectonic or landslide systems? We might expect a stress concentration at the front of the protrusion, and that because of that stress concentration, the material wants to be densified. To densify, water must be expelled from pore spaces. You might elevate pore pressures if that densification, if the force is applied too rapidly for water to move out of the way. And similarly, in the lee or behind the protrusion, the material may dilate and actually have suction stresses, and water might be drawn in. Essentially, we could see all sorts of different things. We might think that upon rapid reactivation of a landslide, these undulations, these protrusions might all be nested within the opposing material. So that might result in the peak strength that people often see upon rapid reactivation of landslides and landslide material. But this undulation, this protrusion should essentially present continuous resistance throughout the movement period. And as it moves, as I mentioned, it should be modifying the material, or could potentially modify the material opposing it. That material needs to deform to allow this to pass, or something else must happen, might have overall dilation or densification of material. So we're going to test these hypotheses using our laboratory observations, those from others, and some numerical modeling. We're going to conclude that undulations do matter. They do contribute shear resistance significantly, but they also modify things such that because of the variable particle scale shear resistance mechanisms for clay and granular material, these undulations can result in catastrophic, accelerating landslide movement, it appears, for material that is more granular rich, non-clay mineral. And for more clay-rich material, these undulations actually may just contribute strength. So we might be able to simply estimate as a first order approximation whether a landslide is likely or not to reactivate catastrophically just based on measures of clay and granular particle content. Let's get into the materials and methods section. And first, I'll just refresh us all a little bit on shear resistance and how we consider it for landslides. Here's a cartoon cross-section of a landslide. And we normally think of shear resistance in accordance with the Coulomb failure rule up here on the top, modified by Terzaghi effective stress. What does that all mean? Well, if you are looking at this, it looks familiar as in high school physics. A friction coefficient multiplied by how hard we press on the surface, right? And that's the total normal stress, essentially the weight of the mass, minus groundwater pressure. So that multiplied by our angle of internal friction, the tangent of that. That's what we use in the Coulomb failure rule for friction coefficient. And we often add C, cohesion, which is something that exists before landslides fail and typically is lost over the first few millimeters or so of displacement. But it's kind of important to recognize that really this friction coefficient and cohesion are really just mathematical constructs. Friction coefficient is stress dependent. Cohesion is stress independent. They really don't tell us anything about what processes are occurring. In fact, there are many mechanisms that feed into both the friction angle and cohesion. When you just get down to brass tacks, I guess, with respect to where shear resistance really, what creates shear resistance, I'll highlight these yellow things down here because these are things that we can measure, we can observe, and we can control during this study. First off, as I briefly mentioned before, if you are going to move particles, you have to move water, assuming a saturated system. And if water cannot move sufficiently rapidly, whether it's trying to fill a void that's being created or evacuate a void that's becoming smaller, you can develop excess pore water pressures that are different from what they were prior to that shear induced movement. The density and packing of the particles is clearly very important as well, and as is because particle surface roughness matters, as does viscosity and thickness of double layer water. Now, those last two bullets there, the highlighted bullets, are where the importance of the material comes in, that the oso material. If we think about clay minerals, especially physicochemically active clay minerals, they have double layer water adsorbed to their surface, such that sodium montmorillonite, for example, which is very active clay mineral, requires megapascal of normal force to actually have contact between the clay particles themselves that double layer water does not want to leave. So that double layer water is actually critical. When it comes to granular material, then the particle surface roughness is much more important. So therefore, changes in density and pore water pressure differently affect clays versus how they affect granular material. And in fact, that different effect is manifested by the friction coefficient and cohesion. Friction is very low for clays relative to granular materials. It's much higher, and the contrary is true for cohesion. So now, as I mentioned, we're going to use lab apparatus, and we use a ring shear apparatus, which there's a cartoon here on the right that shows, well, a cartoon of a ring shear specimen, if you will. This is the specimen inside the apparatus. Half of the specimen, it's ring shaped, and half of it will be held in place, whereas the other half will rotate. So you develop a shear surface or shear gouge, really, between those two sections of the specimen chamber. many people, these ring shear apparatuses have existed for a long time, but they've been significantly improved following the Kobe earthquake in Japan, where they created a new type of ring shear apparatus that provides a number of improvements over the standard apparatus, and in combination are unique. For the purposes of this study, it's important that we have unlimited unidirectional displacement. Essentially, we can shear a gouge for kilometers if we want to. We can control and somewhat, I'll elaborate on that, measure pore water pressure, which is critical. And we have to be able to measure thickness normal to the shear zone accurately, which these apparatuses can do. And thickness in this case would be a proxy for whether dilation or contraction, or an indicator of whether dilation or contraction is occurring. And critically important is that in these apparatuses that we use, we can develop shear gouge on the order of centimeters thick. In other words, similar to what we observe in the field, rather than millimeter thick, as most apparatuses are limited to. Looking in a little bit more detail at the apparatus, obviously here's a picture in the center, and if we just look at one half of that picture in the center, we would have this cross-section cartoon over here on the right, which shows generally how the specimen resides inside the specimen chamber. In this case, the lower half of the apparatus will rotate. The upper half will not rotate, so a shear gouge develops between those two sections. As I mentioned, we can measure and control pore water pressure, but just to some extent, right? Controlling pore water requires pore water to equilibrate through the specimen, both from water supply or drainage on either end of the specimen. And pore water pressure is actually measured outside of the specimen, adjacent to the shear zone, but it is outside of the shear zone, not within it. Okay, so now let's talk briefly about the material that we tested from the OSO landslide. Here's a cross-section of the potential landslide geometry, but the key point here being to illustrate that most of the failure surface occurs in this silt to fat or plastic clay, highly plastic clay. This is a glacial custron deposit, heavily overconsolidated by glacial loading, meaning it's been exposed to much higher pressures in the past than it is now. And because of that, and also because of stream incision or coastal erosion in the case of Seattle, where this unit forms occurs as well and creates quite a bit of landslide problems. Glacial unloading and stream incision has resulted in formation of many faults or shear gouge, shear zones within the formation, as well as fractures. And that includes at OSO and at landslides nearby OSO. And this formation commonly produces some fast-moving, far-traveling landslides in the Seattle area. As I just mentioned, faults are pervasive in some cases, and in blocks within the landslide deposit at OSO, we see slickensides on some surfaces. Perhaps those formed during the landslide, perhaps they pre-existed, but they're pretty pervasive. And we took 3 specimens of landslide for testing, and I'm going to refer to them as granular rather than silt, even though this is a 35 to 50% clay and with the balance being silt formation. The fact that it's granular, not silt size, is what's important, and not active clay. So I'm going to refer to granular material, which had the most granular material, or silt, least clay, a clayey material, which was 50% clay, and a granular clay, which was intermediate in content, had between 35 and 50% clay. We did have mineralogy estimated for this material, and it is rich in sodium montmorillonite, which is a very active clay mineral. But a common way of evaluating the activity of and therefore the effects on shear resistance of a material containing clay is to evaluate the Atterberg limits, plasticity index, plastic limit, liquid limit, by using both the standard distilled water and also with a sodium chloride solution. Use the sodium chloride solution because those free ions that you introduce into the pore water then suppress double layer thickness and therefore increase shear resistance. And we did see a significant increase in plasticity index upon saturation with sodium chloride solution. So we know that it's pretty active clay. And again, to reiterate, changes in density or effective normal stress, essentially how closely packed or compressed the grains in these assemblages are, that's much more important for a granular material and less important for a clay material. So we'll just keep that in mind as we go through the results. So now let's get into our lab testing. Our lab testing began by disaggregating our specimens and drying them, placing them in the specimen chamber, saturating them. The key thing being that these were initially remolded in geotechnical engineering vernacular. The specimens are reconstituted, if you will, which does not represent the intact formation, but it does represent post-peak resistance and also fracture fill. And we consolidated specimens to an overburden or a normal stress of 100 to nearly an order of magnitude higher, 800 kilopascals, which represents a pretty thin to a pretty thick landslide, as you can see there. And we drove these remolded specimens to failure and allowed failure to continue for some meters or tens of meters in order to develop shear gouge. Then we drove shear gouge to failure, first off by increasing shear stress. And we did that at what might sound like a relatively rapid rate, half a kilopascal per second. That's essentially equivalent to 0.02 degrees per second for a given type of landslide. And what we were looking at again was conditions for also during penultimate failure. And again, we would allow shearing to continue until things stabilized, essentially. Most people, as I mentioned, can't do, most apparatuses cannot perform shear stress tests, so we also perform constant shear displacement rate tests, which are very common. And there we sheared over about 5 orders of magnitude of different constant displacement rate tests, and then we evaluated the materials. And here are some photographs of the materials after shearing. For our numerical modeling, of course, we wanted to look at the effects of shearing over an undulatory surface. We used commercial software called Plaxis. It's finite element software. It's very widely used for stress and deformation modeling of soil and rock. I would argue that every one of us has been to a building or driven across a bridge that's partly been designed with the help of Plaxis. It's a pretty impressive package. We model the material as is normally modeled for a soil, as an elastoplastic with Coulomb strength, and using the Terzaghi model of effective stress, and using parameters that are appropriate for the Oso landslide. In fact, many of them are from the immediate vicinity of the Oso landslide. Not that that was important, but we thought that therefore our numerical modeling results would be more correlatable with our laboratory test results. And here's a view of the domain for our model. Basically, we wanted to eliminate edge effects. So we have a very small protrusion. Here it is on the right. Well, first off, let me say we modeled one protrusion. We know that undulations vary in size, spacing, persistence. We don't know anything really about that, or we know some things, but not very much. So we wanted to simplify. Rather than trying undulations, series or a different size, we picked one protrusion. A protrusion has a restraining bend on the front, if you will, with respect to the direction of shearing, and a releasing bend on its back end. In this case, our protrusion is only 1 millimeter high and 15 centimeters long, and it's within a 20-meter thick, 40-meter wide saturated block of material. The protrusion is actually a bump along this impermeable, rigid substrate. So, and then we assigned 2 meters of lateral displacement to the overlying Oso-like material. I need to point out that this is two-dimensional. This is plane strain model. So essentially this protrusion that we introduced is not very narrow as they are in nature, let's say 1 millimeter, centimeter or so thick, but instead it's, well, infinitely thick if our model is infinitely thick, or a unit thickness is essentially treated as infinitely thick. So the effects of the protrusion will be exaggerated rather than if it was just a point, more realistically like a point. And we simulated 4 different scenarios, either undrained shearing across the protrusion or across a planar base with no protrusion. Undrained shearing meaning that we sheared it, we moved the block so rapidly that pore water pressures, excess pore water pressures did develop, shear-induced pore pressures developed, and were not allowed to dissipate at all during the shearing. And in contrast, we also performed the same 2 scenarios, but allowing it to be perfect drained. No excess pore water pressures would develop. In essence, in the first situation, pore water could not move out of the way of moving particles fast enough. In the second situation, pore water could move out of the way and essentially allowed the particles to rearrange themselves freely. Of course, this is a continuum model. It's not individual particles, but essentially that's how that plays out. Okay, let's get into our results. And first we'll look at the gouge from the laboratory. In this photograph here, A, B, and C are looking down on shear surfaces, the top of or somewhere within the shear gouge. Essentially, what I did there was remove the top part, the unsheared material, which was very easy to do in the clay materials. So you see these, and you see these really nice surfaces, and I could get a big exposure here. As granular material content increased, the shear surfaces were not as clear. Here we're looking at our granular specimens in F and G and the granular clay in the middle in D and E. And I think you can see, well, first off, I couldn't really reveal the undulations as well, and they're not as well developed in those as granular content increased. And again, here's that cross section that I showed earlier, but perhaps you can see in a larger view the number of shear surfaces within the shear gouge being this upper centimeter or so. Let's see, striations, as you can see, were common, and oftentimes they were nearly traceable the length of the specimen or the full length that we could expose. And let's see, the undulations, in some cases, they were, less than a millimeter wide, but in some cases, essentially as wide as the specimen. This view in A, perhaps you can see the way that it broke, basically, maybe hopefully I should have pointed that out, but shearing direction, again, since it's cylindrical or it's a ring shear, shearing is essentially parallel to the striations, of course, that you see. But you can see pretty large undulations plus very small striations. Same in B and elsewhere. And many of the undulations were kind of drumlin shaped, and that was much more apparent in the better developed undulations in the clay specimens. Not sure that it's true, but it appeared as though the undulations were larger as clay content increased, but that may also have been just a might just reflect the ease with which those specimens could be separated, or at least the non-sheared could be separated from the sheared material. Also, we observed that the non-sheared material closer to the gouge was more dense than the non-sheared material farther from the gouge, which I'll discuss that in a little bit. Now let's look at some of the model results, and I've kind of put that conceptual picture up here again on the right to kind of compare, I guess, with what we see from the numerical modeling. And recall again that it's plane strain, so the protrusion results are exaggerated because you may see some very high stresses here. This plot here shows the difference in principal stress, sigma 1, between the protrusion scenario and no protrusion scenario. And you can see these purplish colors, those mean that stress increased. The principal stress increased, well, dramatically in some cases, very near the protrusion and in front of the protrusion. In contrast, behind the protrusion, stress decreased. The principal stress decreased, so there was less there, similar to what we imagined from our conceptual model. And somewhat similarly, we can look at strain and as a proxy essentially for consolidation or dilation. This plot shows volumetric strain. So in front of the protrusion, essentially the strain was negative, meaning material was consolidating or collapsing, as we might have imagined from the very high positive stress increase in front of the protrusion. In contrast, behind the protrusion, where stress is decreased, the material dilated, or it increased in volume. And similarly, again, as you might imagine, again, because of that stress increase in advance or in front of the protrusion, pore water pressure was elevated as well, in front of the protrusion and actually throughout the domain, except in that region where dilation and a stress drop occurred. In that case, we had negative pore water pressure, suction stress, essentially. And of course, we can put our total stress together with our pore water pressure and look at our effective normal stress. And recalling again that controls our shear resistance. And we can see that above and in front of the protrusion, the effective normal stress increased pretty significantly, whereas behind the protrusion, the effective normal stress decreased significantly in some cases. And then if we just look at things in terms of the total force required to move that block across the protrusion, we see that, in fact, as expected, the protrusion contributes shear resistance. It contributes, if we allow the material to deform by having the shearing occur slowly, there's 5 times less, let's say, increase in force required than if we don't allow the material to deform as much and force that displacement very rapidly. And in overall terms, if we move the block rapidly compared to slowly, there's actually less force required, suggesting that dilation and effective normal stress reduction behind the protrusion contributes to lower resistance in its lee or behind it. I should point out, though, with the changes in strain that we saw from the model, that did not affect the shear resistance in the model itself. So that's, you have to consider that results in these results being a bit exaggerated. Okay, now let's look at some of the laboratory results. And I know that this is a pretty noisy plot. It's a time series plot, time on the x-axis, and several things on the y-axis. But what I guess I'd like you to focus on is, first off, the red. That's the shear stress that we're applying to the specimen. And as you can see here, shear stress is increasing. At that same time, this orange line, that shows shear displacement. As that shear stress increases, we're seeing some little creeping failure on the order of less than a millimeter until failure really occurs and the shearing accelerates. There's a top end governor on the system, but acceleration is allowed to occur until it reaches that top end. So as this displacement is occurring and shear resistance is dropping, because the shear stress applied by the apparatus can only reach the shear resistance of the material, we see that by the brown line, the specimen dilated significantly. It increased in thickness during that decrease in shear resistance. And as shearing progressed, though, that dilation was reduced until eventually the material thinned. And after we stopped shearing, which is indicated here, just no more displacement. And when we opened the pore water drainage lines for the specimen, additional consolidation or thinning occurred. Somewhat similarly, from our constant shear displacement rate tests, we noticed that specimens contracted or thinned when they were sheared below about 1 millimeter per second. And that's shown by these 3 lines here. The clay specimen in black and the granular specimen is black dashed. But at rates higher than 1 millimeter per second, the specimens dilated. And you also can recognize that clay gouge dilated the most. Again, this kind of goes back to the necessity for water essentially to move out of the pore spaces to allow deformation to occur. Although the shear rates may be the same, the clay hydraulic conductivity should be lower than that of the granular material, and therefore the relative scales of displacement versus water movement are different. So clay should dilate more than granular material. Now let's consider pore water pressure during shear failure. Here's a different test, and again, we're increasing shear stress. until failure occurs here. And you can see then, from that creeping failure up to, again, about a millimeter of creeping failure, then we have an accelerating failure as the shear resistance dropped pretty dramatically, dilation occurring again, and accompanying that drop and dilation was a reduction or suction of pore water pressure. We saw a negative pore water pressure. However, after we stopped shearing, pore water pressure recovered again to some positive value. And we saw that every time when we would stop shearing, that regardless of whether pore pressure was positive or negative, it would always rise and then stabilize at some peak value after shearing ceased. And then we can evaluate something similar from our constant shear displacement rate tests, and that's what this chart does. I would focus on the black rather than the gray lines here in the plot. As we just saw in that last chart, and the previous, pore water pressures during shearing were pretty unstable and irregular. They may have been positive, negative, gone back and forth. And in fact, the pore water pressures during shearing at these constant shear displacement rates are shown in gray, and you can see the linear fits are very poor. So let's ignore those. But what there's better fit to is that peak pressure that we observed after shearing stopped. So essentially, or we can see in that case that there's a much better fit. The R-squareds are, well, 0.5 is not great, but 0.8 and 0.9 aren't too bad. So we have a better linear fit. And again, we see that we develop higher pore water pressures in the clay, similar to it dilating more, the clay dilating more at a given shear rate as compared to the more granular-rich material. Okay, now let's talk about shear resistance. So it's just focusing on processes alone. And I just want to point out, as I pointed out with one of the first slides, that we did, in fact, during this relatively rapid change in stress, we had a peak strength and a strength that decreased after that peak. Well, that's kind of the definition, right? We had an initial peak strength and then a strength decrease thereafter, as has been observed by many others. And again, that decays to a final level, usually within a few centimeters of displacement. Now let's talk about the actual resistance terms that we observed and what we saw. First off, the granular gouge was weaker and it lost more resistance than when it was remolded. Okay, and that's obviously shown in this table here. Its peak resistance is lower as gouge, and its ultimate resistance is lower as gouge. And we can think about the processes required or that result in a drop in strength with a remolded condition. That's alignment, comminution of particles, smoothing, that sort of thing, and densification that can result in pore water pressure change. That's in the granular when we're going for, in the remolded sense before we have gouge. Once we have gouge, we should have a relatively consistent shear zone. At least that's how it's typically considered. But we see, obviously different strength responses for the granular material, whether remolded or as gouge. And similarly, also, we see differences for the clay and the granular clay. We see in those cases that they were stronger and lost less resistance when they were gouge compared to as remolded. So a total contrast in change in resistance with change of the material when comparing clay to the granular material. And I'll describe why that may be in a moment. And also, of course, the gouge resistance decreased the most for granular material, and it decreased the least for clay gouge compared to the granular gouge. Somewhat similarly, from our constant shear displacement rate tests, we see that the granular gouge resistance, the granulars and the dashed lines here, it decreased the most with increasing shear rates. You can, for instance, at 200, these numbers following in the legend are the normal stresses applied to those materials. So we see shear resistance dropping with increasing shear displacement rate pretty dramatically for the granular-rich gouge, and not so dramatically for the clay-rich gouge, in fact, increasing in some cases. Okay, so now let's get into the discussion and talk about what these results mean. I know there are a lot of results there, but I do like to separate the results from the discussion. So As I showed before, of course, the stresses appear to redistribute themselves. We can't look at the stresses at a protrusion scale in the lab test. But from the numerical modeling, we can see that the stresses change pretty dramatically. That's directly shown by the modeling with a stress elevation in front of the protrusion or by the restraining bend, and stress reduction behind the protrusion or by the releasing bend. And that's directly showed by the modeling, but we also saw that the material was more dense in the lab, nearer to the gouge than it was farther away. And we can imagine that that might have occurred because of this high increase in stress in front of the protrusion that would cause stuff outside of the shear zone to densify. Um, Similarly, during our constant shear test, constant shear rate test, we observed that the specimen is thinned. In that case, one can assume that since the shearing was occurring more slowly, water is more able to move out of pore spaces, and therefore the material's more able to deform and therefore thin, because that's what it wants to do there. It wants to consolidate again because of these high normal stresses. And also, even during the rapid tests that we allowed to go to many meters of displacement, those specimens, even though they dilated initially, they thinned eventually. And perhaps we might assume there that that dilation was occurring throughout, but thinning was also occurring throughout, and dilation was finite, whereas the thinning was able to continue as the material continued to densify outside of the shear gouge. Okay, again, shearing across this protrusion requires deformation. And we see that directly from the volumetric strain modeling results, where material contracted again in the high stress region in front of the protrusion and dilated in the low stress region or the decreased stress region behind the protrusion. And similarly, and essentially accompanying that, pore water pressures were elevated in front of the protrusion and decreased behind the protrusion. And essentially, basically these modeling results are reinforced by laboratory results as well. We saw dilation when rapid failure would occur, and upon essentially just like we see here with consolidation and dilation, or dilation in this region. And we saw negative pore water pressures adjacent to the shear zone in some cases during shearing, probably because those regions were dilated. The specimens were thicker and the pore pressure dropped adjacent to the shear zone, presumably again because of that region being dilated, because the shearing was occurring much more rapidly than pore water could move to fill changing pore spaces. And again, after shearing ceased, in all cases, we saw positive pressures throughout the specimens, which, as we see in the plot here on the right, the modeling suggested we should have seen a lot of positive pressures. Well, again, we're measuring them adjacent to the shear zone, so once the pressures could equilibrate after shearing, we would see those positive pressures. And we also saw consolidation every time when we stopped shearing. And again, presumably because they were dilated from shearing, that was induced by shearing, and that consolidation occurred when that dilation relaxed. So with respect to resistance, we can say that these undulatory surfaces present geometric interference to shear displacement. We see that directly from modeling, and our own lab tests, as well as those of others, show a higher peak resistance initially during rapid failure. And we think that that might be because the undulations essentially nested during consolidation. During the period when no shearing is occurring and material can't consolidate, essentially these wavy surfaces are nesting within one another. So upon renewed rapid failure, those undulations unnest essentially, and that results in dilation, and also introduces that peak resistance. And some apparatuses that can involve or can measure vertical deformation besides ours also have observed dilation, commonly occurring during the initial parts of renewed failure and under rapid stress conditions. As I mentioned, we saw that the clayier material had higher peak resistance when it was gouge compared to when it was remolded, which really doesn't make much sense from what we know about things changing, unless it's really caused by undulations that are nesting or pushing through, plowing through the opposing material. Because the gouge was developed, that peak from during remolded conditions existed because particles were misaligned and rougher and larger and that sort of thing. So the peak resistance that occurred in the gouge may have resulted from nesting of those undulations. In contrast, the granular gouge had slightly lower peak than remolded, which makes some sense, again, because the grains themselves were smooth and aligned in the granular gouge compared to as remolded. And the undulations didn't seem to be as well developed in the more granular-rich gouge. Again, the peak resistance, or in some though, the peak resistance for the clay gouge was highest and lowest for granular gouge, which is opposite what we know for clays and granular materials when they're not in a gouge form. And again, this points to nested undulations creating that peak, and also because they're better developed and seemingly larger with increasing clay content. So it seems pretty clear that these undulations might add resistance, but again, they change the stresses in pore water pressure and material density that can modify the resistance of the particle system around the gouge or within the gouge as well. And as you know, indicated by these plots before, effective normal stress being decreased behind the protrusion, and dilation or density, dilation occurring behind the protrusion, so the density decreases. If the density decreases, our friction coefficient decreases, and our cohesion may as well. And if the effective normal stress decreases, well, this term decreases as well, so our shear resistance drops behind the protrusion, and it may increase in advance of the protrusion. So you have these very complex effects that, again, should matter differently depending on whether it's a granular material or a clay material. And in fact, that's what we saw, that the final resistance of the granular gouge was lower than when it was initially remolded, which is meaning that the undulations, the shearing across undulations, are apparently changing the density and the effective normal stress sufficiently in the granular material to weaken it significantly. And that's because granular material experiences those true particle contacts. In contrast, the undulations in the clayier material had created more resistance and didn't modify effective normal stress and material density sufficiently to reduce the particle scale resistance. And again, that's really because those particles, especially the montmorillonite particles, weren't experiencing true particle contacts. And also double layer water doesn't transmit pore pressure. So again, those changes don't really affect clays very much. When we consider both the peak and the final resistance or the ultimate resistance, again, we can see that well, let's talk about resistance retention. How much strength is lost? That's really what's important with respect to whether a landslide is going to move rapidly or slowly or not at all, essentially. And the granular gouge resistance retention, it was lower than when it was remolded. So here in black, basically, the granular gouge lost about 40 to 44% of its strength, or retained 44% of its strength, whereas the when it was in a remolded sense, it retained more strength. By contrast, for the clayey material, more strength was retained as gouge than as remolded. So those undulations, again, just contributed much more resistance to the clayier material and didn't really contribute to lower particle scale resistance. So we see that pattern there. Let's see. So in sum, I guess, I know that's a lot of information that it's hard for me to get through. But what we see that these undulations apparently contribute an initial peak resistance that exists at the onset of renewed rapid failure. And in some cases, people refer to something like this as healing, with mechanisms unknown other than physical chemical bonding and maybe cementation, things of that nature. The undulations, though, also instigate particle scale weakening because of dilation and effective normal stress reduction by releasing bends, essentially. And for granular-rich material, that matters. So in granular-rich material is more likely to weaken from shearing across undulations, whereas clay-rich material is overall more likely to be stronger. Now, those are the results from our tests and our modeling, but what about other materials? This is 3 specimens from 1 geologic formation. So, as I mentioned, the apparatus that we used is pretty uncommon. Most people can perform constant shear displacement rate tests, as we did as well. So that's how we'll compare our results to other people's results. So just to refresh what we saw, that the granular gouge essentially lost up to half of its resistance as shear rate increased over about 5 orders of magnitude, whereas the clay gouge gained some resistance to lost about 10% over that same change in shear rate. So again, the granular gouge lost a lot of strength, clay gouge not so much. Well, we looked at 117 different materials that people have tested around the world, materials from landslides, tectonic faults, and synthetic materials, mixtures of specific ideal materials, if you will. And these tests were performed with a huge variation in laboratory apparatuses and normal stresses, in some cases getting into the tens of megapascal. And here's what we saw. We can, if we classify those test results by just the size fraction of the material that they tested, we saw that if there was very little clay, their resistance was unchanged with increasing shear rate or decreasing shear rate. It's unchanged resistance with variable shear rate. However, if you add some clay, the materials tested by others experienced weakening as shear displacement rates increased, which points to accelerating failure. And if you add even more clay, though, those materials with highest clay content, exhibited strengthening as shear rates increased. And also plotted on here, I've just shown where our materials are that we tested. We can look at this another way. In this case, we lose a few materials because we're looking at plasticity index. Because plasticity index is a decent proxy for clay activity and also the clay content, clay size fraction, and clay mineral fraction, especially in these materials. And again, with low plasticity index, others observed unchanging resistance with variable shear speed. Whereas if some clay was added, the resistance decreased. I'm sorry, if the plasticity index increased, the resistance would decrease with increased shear rate. And for highly plastic materials, physical-chemically rich clay materials, the resistance increased with increasing shear rate. When we sum all of this up, we observe that these undulatory shear surfaces appear to introduce geometric interference that contributes resistance, provides a mechanism for healing, and peak resistance that occurs during rapid stress changes. During those rapid stress changes, undulations elicit changes to the stress regime and the particle assemblage nearby, and they can create a persistent pore water pressure change throughout the shear displacement history. So therefore, creating a mechanism essentially for accelerating or decelerating failure, and that relates directly to weakening or strengthening with increasing shear rate. So we can conclude then that ongoing accelerating landslide reactivation is most likely with granular-rich clay pore gouge, and the contrary is true as well. Decelerating landslide reactivation should be expected with clay-rich shear gouge. And of course, these findings have implications for other sliding systems, such as tectonic faults and glaciers, things of that nature. So that's a lot of stuff. I'll try to wrap up real quickly with a conclusion here. The reason for the study, essentially, let's boil it back to some landslides fail rapidly when they're exposed to rapid changes in stress, even though they move slowly under gravitational conditions. And we need to understand why that might occur. We hypothesize that the shear surface undulations create geometric interference that modifies shear resistance, and we test with numerical modeling and laboratory observations. And let's see, we understand that these undulations might result in a peak strength appearing on renewed failure, and higher resistance than when they don't exist. Shearing across the surfaces change the resistance essentially of material nearby, but they change the resistance of granular material much more strongly than they do clayey material. And therefore, these surfaces might explain catastrophic landslide movement from rapid changes in stressing, and those should really be occurring more in gouge that's more granular-rich. And our observations, again, might help to explain characteristics of other sliding systems. Thanks, that's it.